For millennia, they were terrifying. Just imagine the sun gone in the middle of the day.
Or the moon turning this deep blood red color.
Yeah. What is some, I don't know, cosmic beast? Angry gods?
Or maybe something else entirely. Something, well, predictable.
Something like geometry, which is where Aryabhata comes in. He looked up and saw not just myths, but maths.
An answer woven into the fabric of space itself.
Welcome back, everyone, to the deep dive.
Hello again.
We are pushing forward with Aryabhata, building on what we talked about last time, how he measured the sky, right? That whole spherical model.
And those crucial Dṛkkarma corrections, we cover the ones for altitude parallax, horizon dip, how height changes things.
Exactly, but finding something in the sky isn't just about how high, it's also where along its path, its longitude.
Especially near the horizon. Things get tricky there.
So today, we're diving into two more of Aryabhata's corrections. These ones are all about refining that longitude.
Getting the east-west position just right.
Greetings, fellow travelers, fellow eclipse enthusiasts, and maybe mythbusters. Welcome back.
Glad to be continuing this.
Last time, we saw how Aryabhata dealt with our viewpoint, the Earth's curve, our angle using those Dṛkkarma, those visibility corrections for altitude.
Parallax and horizon dip, yeah.
But the view is more complex than just up and down, isn't it? Today, it's longitude, the east-west. And these really subtle adjustments Aryabhata figured out were needed.
To make the calculations match what we actually see from Earth.
Okay, let's really get into the weeds here, in a good way.
Definitely. These next two sound complex, Akṣadṛkkarma and Ayanadṛkkarma.
Right, like ancient riddles. And yeah, the math involves some serious trigonometry.
But the core idea, it's about perspective. How do we, standing on this spinning ball, accurately map things moving across another sphere, the sky?
Especially when they're low down where our view gets warped almost.
Exactly. So verse 35 gives us the first one, Akṣadṛkkarma.
How do you pronounce that again?
Akṣadṛkkarma.
Akṣadṛkkarma.
Okay.
Often called the latitude-visibility correction.
And what's amazing right away is Aryabhata's grasp of perspective. He knew that where you are on Earth changes what you see up there. Your latitude matters.
So it's not a one-size-fits-all view of the cosmos. This correction is his way of mathematically accounting for your specific spot on the globe.
Pretty much. He's saying your latitude influences your perception of celestial longitude.
Okay, so the verse, in a simplified sense, talks about taking a few values. Something related to the object's own latitude up in the sky.
Right, it's celestial latitude, how far it is north or south of the ecliptic. We call that vitāpa.
Vitāpa.
Got it. And you multiply that by something related to our latitude, the observer's latitude.
Yeah, the Akṣa, S-A-K-Ş-Y-A. Think our scene of the observer's latitude.
Okay. And divide by another value linked to observer latitude.
The Lambaka, Alambaka, essentially our cosine of the latitude.
Right. And the result? You add or subtract it. Depends. North or south hemisphere. Is the object rising or setting? He specifically notes it's quite important for the moon.
So let's unpack that. This Ayanadṛkkarma is basically dealing with the interplay between two angles.
Exactly. Angle 1. The object's celestial latitude, it's up-down relative to the sun's path, the ecliptic.
Okay, Vitāpa.
Angle 2. Your terrestrial latitude, your up-down position here on Earth. Akṣa.
Okay.
Now picture looking at something not directly overhead. Your line of sight is angled. This correction accounts for how that angle, affected by both the object's position and your position, slightly shifts its apparent east-west location.
It's longitude.
Yes, it's longitude. And the effect is most noticeable when the object is low, near the horizon.
It's kind of like if you're standing on a sloping beach, trying to judge where a boat is horizontally out on the water.
That's actually a really good way to think about it, yeah.
The slope of the beach, your latitude, and how far the boat is from some center line, its celestial latitude, both affect how you perceive its side-to-side position.
Exactly. A nice analogy.
And you mentioned he flags the moon Candra, as being particularly important here. Why the moon?
Well, think about the moon's orbit. It's tilted slightly compared to Earth's orbit around the sun, the ecliptic plane.
Okay, right. About 5 degrees, isn't it?
Something like that. So the moon's celestial latitude, its vitāpa, changes quite a bit as it orbits. Much more than the sun, which defines the ecliptic.
Ah, so because the moon wanders further north and south of that main path.
The interaction between its latitude and our latitude becomes more significant. It leads to a more obvious shift in its apparent longitude, again, especially near the horizon.
Wow. So him pointing out the moon specifically shows he wasn't just making broad strokes. He was noticing the finer details of how different bodies behave.
Absolutely. It shows a real sensitivity to the specific mechanics. He's comparing calculations to actual observations and refining things.
Which really highlights the precision he was aiming for. It wasn't just theory, it had to match reality. Okay then, verse 36 brings in the next one. Ayanadṛkkarma.
Ayanadṛkkarma.
Ayanadṛkkarma. Right. This translates roughly as ecliptic inclination correction. And the verse here, again simplified, involves multiplying a latitude-related value by something linked to the object's declination or its verse sign.
Declination being its position north or south of the celestial equator this time, not the ecliptic.
Right. And then you add or subtract based on the season, the ayana, and where the body is.
Exactly. So here, Aryabhata is tackling another layer of geometric complexity.
Which is?
The fact that the ecliptic, the sun's path, isn't lined up with Earth's equator. It's tilted.
The famous 23.5 degrees. That's what gives the seasons, right? Ayana refers to that seasonal shift, the sun's north-south movement.
Precisely. Now imagine that tilted path stretched across the sky. When you look at something near the horizon, the angle at which that tilted ecliptic meets your local horizon changes.
Ah, okay. And it changes depending on your latitude and the time of year.
And the time of year, yes. Because of that tilt, think about sunrise or sunset.
The angle is different in summer versus winter.
Exactly. And that difference affects how we perceive the east-west position, the longitude of other objects near the horizon at those times.
So Ayanadṛkkarma is correcting for that distortion, the one caused by the changing angle of the ecliptic against our horizon through the seasons.
Yes, and it also factors in the object's declination, its position relative to the celestial equator. It's knitting together the Earth's tilt, the seasons, and the object's position relative to the equator to refine the longitude calculation.
That is incredibly sophisticated thinking for the 5th century. Understanding how all these different planes and angles interact from our perspective on Earth.
It really is. It shows a deep grasp of spherical geometry and the dynamics of the sky.
Yeah, okay, so let's zoom out. We've got these altitude corrections, parallax, horizon dip from last time, and now these 2 longitude corrections, Ayanadṛkkarma. What's the big payoff? Why obsess over these, well, seemingly tiny adjustments?
Because they weren't tiny adjustments if you wanted accuracy. These Dṛkkarma corrections, taken together, show Aryabhata wasn't just guessing. He was a meticulous observer and a really advanced geometric thinker for his time.
They weren't just fudging factors.
Not at all. They flowed directly from understanding a spherical Earth within a celestial sphere, and how our specific location and the time influence our view. It demonstrates, implicitly, a mastery of spherical trigonometry.
And this level of precision was absolutely essential for
It's eclipses. Exactly. Think about what an eclipse is.
sun, moon, Earth lining up perfectly.
Perfectly. Or very, very close to it. Tiny errors in calculating where the moon is, its longitude, especially near the nodes where its path crosses the ecliptic, would completely throw off predictions.
You miss the timing or predict visibility in the wrong place.
Or get the duration wrong, or how much of the sun or moon is covered the magnitude. Without these Dṛkkarma corrections, Aryabhata's eclipse calculations just wouldn't have worked as well as they apparently did.
It's like fine-tuning an incredibly sensitive instrument. Every little wobble needs to be accounted for.
Precisely.
And with this amazing framework built spherical cosmos, rotating Earth coordinates, measurements, and now these crucial visibility corrections, Aryabhata was ready to tackle eclipses themselves.
Yes. And that brings us to verse 37 in the Golapāda, a truly pivotal moment.
This is where he drops the bombshell, isn't it? His revolutionary explanation. The translation goes, the moon is water, the sun is fire, earth is earth, and the shadow indeed is darkness, Tamaḥ. The moon covers Chārayati, the sun Sūrya, and the great earth shadow, Mahati Bhūcchāyā, covers the moon.
This verse is just huge. Let's break it down. The first part. Moon is water, sun is fire, earth is earth.
That sounds familiar, like standard elemental associations of the time.
Exactly. It probably reflects the common cosmology linking celestial bodies to elements. It sets the stage, kind of grounds it in familiar ideas for his audience.
But then
the critical part. And the shadow, Chāyā, indeed is darkness, Tamaḥ.
Chāyā is shadow, Tamaḥ is darkness.
Yes. And look how direct it is. He's defining a shadow, not as a demon, not as a god's anger,
but as darkness, Tamaḥ, the simple absence of light.
It's a physical definition. Instantly demystifies it. All that superstition around eclipses. He's just sweeping it aside with basic physics.
Right. Forget Rāhu, R-A-A-Hu, the mythical demon head swallowing the sun or moon. That was the prevailing story, right?
In many traditions, yes, a very powerful myth. Aryabhata replaces it with observation and geometry, pure physics.
And then he nails the mechanics for both types of eclipse, clear as day or night.
Absolutely. For a solar eclipse, the moon, Śaśī, covers Aryabhatiya, the sun, Sūrya.
Śaśī covers Sūrya. Simple, accurate. The moon gets between us and the sun. It casts its shadow on Earth.
Perfect geometric description. And for a lunar eclipse, the great Earth shadow, Bhūcchāyā, covers the moon.
Bhūcchāyā, the great Earth shadow. Again, purely physical. Earth gets between the sun and moon. Our planet's shadow falls on the moon.
It dims, it turns red, it disappears into that cone of darkness cast by Earth.
This must have been mind-blowing, to just ditch the mythology and say, nope, it's just shadows, folks. An incredible intellectual leap.
A monumental shift in thinking. From gods and monsters to spheres and light rays.
And like we've been saying, this explanation didn't come out of nowhere. It relies entirely on the groundwork he already laid.
Absolutely. You need a spherical Earth Bhūgala, B-H-O-Gala, to cast that big cone-shaped shadow into space. That was Gola verse 5.
Right, an opaque Earth.
And an opaque sun and moon, too. One gives light, the others block it.
And the idea of one body covering another implies he understood their relative sizes, their distances, their movement in 3D space.
Yes, and that relies on his understanding of their motions, which he detailed earlier, especially in the Aryabhata section. Knowing how they move is key to knowing when they'll line up.
So it all connects. The spherical model, the motions, the opaqueness.
Yeah.
It all leads logically to this shadow explanation.
It's a cohesive, rational system. Observation, geometry, and physics working together. No need for supernatural actors.
It really marks a turn, doesn't it? From seeing these events purely as omens or divine signs.
To seeing them as predictable phenomena governed by natural laws. Think about the courage that took.
Seriously, to challenge centuries, maybe millennia, of deeply ingrained belief with, actually, it's just geometry and shadows.
It's a fundamental reframing. It takes astronomy firmly out of the realm of pure divination and puts it squarely into physics and mathematics.
And it sets the stage for everything that follows in his work on eclipses.
Exactly. Once you establish the why it's shadows, you can then focus on the how.
How to calculate them.
How to predict when the alignments happen, where the shadows will fall, how long they'll last, what they'll look like. That becomes the next challenge.
The mathematical challenge.
Yes. Verse 37 provides that essential physical foundation. Now the calculations can begin. It's a huge step towards predictive science.
And it's just amazing that this core principle from Gola 37 eclipses are caused by shadows cast by the moon and Earth is still exactly how we understand and predict them today.
Absolutely. Fundamentally, nothing has changed about the why. When astronomers today predict an eclipse down to the second, mapping the path of totality across the Earth.
They're using the same basic idea Aryabhata laid out. Sun, Earth, moon alignment, geometry of shadows.
Our tools are just vastly more powerful now. We have incredibly precise measurements of orbits, gravity models, computers crunching numbers.
We can send probes up there to watch.
Right. But the underlying concept, identical. It's still about calculating when and where the moon's shadow hits Earth, or when the moon enters Earth's shadow.
The precision is breathtaking now, but the framework is ancient. It's kind of humbling.
It is. And it's not just for predicting eclipses we see from Earth. Think about space exploration.
How so?
Well, satellites orbiting Earth often pass into Earth's shadow, right?
Yeah, happens all the time. An occultation.
Exactly. And if that satellite relies on solar panels for power, suddenly no sunlight.
Uh-oh. Power drain.
Mission planners have to calculate these shadow crossings, these occultations, with extreme precision. They need to know exactly when the satellite goes dark and for how long to manage power, maybe switch to batteries, pause certain operations.
So calculating the Earth's shadow is critical for satellite operations.
Definitely. Or think about scientific observations. Sometimes a spacecraft will use the shadow of, say, Jupiter or Saturn passing in front of a distant star.
Why would they do that?
As the starlight filters through the edge of the planet's atmosphere just before or after the main occultation, the light changes. Analyzing those changes tells scientists a lot about the atmosphere's composition and structure.
Wow, so they use the shadow or the edge of it as a tool.
Precisely. And again, that requires incredibly accurate calculations of the shadow's geometry and timing. It all comes back to understanding how these celestial bodies block light.
That's a fantastic link. Aryabhata's basic insight has these really practical high-tech applications today. His rejection of myth for physics wasn't just philosophy.
It was foundational science. It paved the way for this incredibly powerful system of understanding the cosmos that lets us predict events and navigate space.
His focus on observation, on geometry, on finding natural explanations. That's the heart of science then and now. It connects across the centuries.
It truly does.
So this deep dive has been, wow. We've covered those intricate Dṛkkarma corrections showing his drive for accuracy.
Seeing how he refined both altitude and longitude based on perspective.
And then we hit verse 37, the big one. His rational, shadow-based explanation for eclipses. A clean break from mythology.
Establishing the physical why. Why do eclipses happen?
Because of shadows cast by celestial bodies.
Okay, so we know why Aryabhata thought eclipses occurred, but that naturally leads to the next question, right? The one he tackled next.
Which is?
How do you actually calculate them? Now that you know it's shadows, how do you predict the details? When? How long? How much coverage?
Ah, yes, the practical application.
So join us next time on The Deep Dive. We're going to get into the nitty-gritty of Aryabhata's eclipse calculations, how he figured out the size and shape of Earth's shadow way out at the moon's distance.
And the mathematical framework he built to predict the timing, duration, and magnitude of both solar and lunar eclipses.
Get ready for some beautiful applied geometry, the geometry of cosmic shadows. You really won't want to miss it.
See you then.